Our next presenters, this is their first time presenting at an Information Security Con, first time speaking at ShmooCon. So please give a warm welcome to these 3 gentlemen that will be speaking on the phantom of the pipeline, abusing self-hosted CI/CD runners.
All right, thank you everyone for coming to our talk. We're so excited to present some things that we think is pretty cool, and we hope by the end of the talk you guys will agree as well. So, our talk is Phantom of the Pipeline, abusing self-hosted CI/CD runners, but mostly GitHub in this case. Who are we? So, my name is Adnan Khan. I am a lead security engineer at Praetorian, and I'll let the rest of the team introduce themselves.
Hey, my name is Mason Davis. I'm also a lead security engineer at Praetorian.
And I'm Matthew Jackoski, again, a lead security engineer at Praetorian. So I'll start us off. Just kind of some general, I guess like vocab. Make sure everybody's kind of coming into this with the same set of knowledge. So as we mentioned, we're abusing, in this talk, self-hosted runners, and in this case, GitHub. So this is really compromising CI/CD, which is continuous integration, continuous delivery platforms. For those who don't know what CI/CD is, really it's just a way to automate building, testing, and deploying software. CI/CD typically involves workflows that execute pipelines. There's many triggers that can trigger a workflow, but one of the more common ones would be a push to a code repository. So looking at this diagram, you can see a developer makes a change to code on their local machine. They push that to a code repository. For the sake of this talk, we'll say GitHub. And a workflow is triggered, which this workflow then is picked up by a runner, which then executes that job, which can be many different things, such as updating documentation, building the code, etc. There's many different tools which implement CI/CD. Some of the more classic ones would be Jenkins or TeamCity, and some of the more modern ones being GitLab and GitHub Actions. So as I mentioned, GitHub Actions, GitHub is the focus of this talk, although this concept can be kind of ported over to many other CI/CD platforms. So what is GitHub's implementation of CI/CD? It's called GitHub Actions. If you go to any repository within GitHub, it will have an Actions tab, which is where all of the workflow information is. Typically, these workflows are defined in YAML files found in the .github/workflows directory. And these YAML files are broken down into jobs, which are then dispatched to runners. There are 2 different types of runners that GitHub supports, or 2 different options. One is the ephemeral host, which are actually managed by GitHub. And then they also support the self-hosted, which are managed by the customer. And that's going to be the focus of this talk. So why do companies use or developers use self-hosted runners? There's really a number of different reasons. One being cost saving. So with GitHub, each organization is allotted a certain amount of billable minutes within or on the self-hosted ephemeral GitHub runners. But after you hit this minute limit, okay, thank you. So take a step back. One of the reasons we use self-hosted runners is for cost saving. Organizations are set a billable limit, and once they reach this billable limit, if they're using ephemeral runners hosted by GitHub, then it begins the costs add up very quickly. Additionally, another reason for self-hosted runners is it provides more customization options. They can interface with hardware, GPU, etc. And they can handle a larger workload. You can make these things as beefy as you want. And then one of the more interesting things here is that you can host these self-hosted runners on premise, meaning that they can access resources on your local network that GitHub runners would not be able to do without any sort of proxy, etc. How do these runners work? So they're just a .NET Core application. They run on Linux, OS X, Windows, etc. And by default, these self-hosted runners are not ephemeral. There is a way to configure that, but the setup is more complex. And when I say not ephemeral, I mean the jobs execute directly on the host operating system. Of course, there is cleanup afterwards, but it's still executing on the host itself. The setup is very turnkey. It's just a zip or tar file. You extract it, configure it to sync with the GitHub repository or organization, and you run it. Before we go too much further here, GitHub does denote that these self-hosted runners can be very dangerous. This is straight from their documentation. So there is significant risk to the machine and whatever network that they're on. GitHub calls this out as risks for initial access, sandbox escapes, persistence within a network, and even lateral movement, which is something that we will show in a few slides. Now, one more thing that we want to go over before we get into how you abuse self-hosted runners is, what is a GitHub personal access token? So we refer to them as PATs commonly throughout this talk. Essentially, it's just an API bearer token that you can authenticate to GitHub with. They're associated with the account that created the PAT. They can have many different levels of permissions and are used for creating, managing repositories, pull requests, managing issues, managing workflows, etc. Additionally, these PATs can be revoked at any time. So that's a great thing for developers. If a PAT is ever compromised, they can be revoked in the GitHub UI. And I believe at creation, the standard is a 7-day period that they last. However, this can be customizable to never expiring or expiring in just a day. There are two types. We'll get into this a little bit later, but there's the newer type, which is the fine grain token, which is still in the beta. And then there's a classic token, which is what we'll talk about. So GitHub Actions, CI/CD, PATs, how does it all come together in an attack path? So the three of us are red teamers, and we have been really focusing on CI/CD for about the last year. And this is an example attack path that we've executed on multiple red teams over the year. At a high level, there's really 6 steps here. It's first, you try to socially engineer a developer or really anyone in an organization that might have access to some way to get a PAT. And when I say some way, this could be, if they're a developer, somewhere on their machine in like a home directory or bash history backup. This could be anyone that has access to artifacts within that network. PATs are very commonly pushed into artifacts or Docker containers and then kind of just forgotten. So we go through the social engineering aspect, we obtain a PAT. The next thing we do is we can use this PAT to enumerate the GitHub API to learn exactly what permissions are associated with it, and we can begin to look for repositories that use self-hosted runners. At this point, once we identify a repository that is vulnerable or is using a self-hosted runner and we have at least repo access to, we can push a malicious workflow to that repository, which is then triggering a workflow that's picked up by one of those GitHub runners. Now, during execution, after a workflow executes, there is a cleanup. There are many ways to kind of persist after that cleanup. In the case of this example attack path, we just start a detached Docker container, which then persists past when the workflow has ended execution. So after we get that detached workflow running, it's profit. We now have C2 on that organization's local network, coming from a completely external SaaS application. Some ideas for targeting developers to obtain PATs would be, there's pretty common for developers to install tools with just a curl, some totally trusted domain, pipe that right to bash, and then lo and behold, we're trying to scour their system, exfiltrate cookies, and see if we can get anything from bash history, etc. Additionally, there's the phishing campaigns that are pretty classic to red teams, trying to get access to Okta dashboards or any other SaaS applications. And then once we have access to this, we look through Slack or Teams or any other type of messaging software. If we have access to logs or artifacts, trying to scour through, find secrets. And very commonly, that's where we'll find a PAT. For finding these secrets, I kind of mentioned this earlier, but it's really just secret scanning, home directory backups, Git commit history we've had a lot of success with in the past, sensor logs. So if you somehow get access to EDR logs, that's command line history that's right there. You can comb through that. PATs are very commonly committed to command line history. CI/CD artifacts, if you get access to a unauthenticated JFrog instance, for example, you can start just dumping all of those artifacts and looking through there. There's many ways to scan for this. One way that we commonly use is we do work at Praetorian, so we released a secret scanner called Nosy Parker pretty recently that we've had great success with. There's many options out there though. So at this point, I found a PAT, now what do I do with it? So now we come to the time to start enumerating. And for that, I will let Adnan speak.
All right, so once you've obtained a PAT, at that point you don't know if it's valid or if it belongs to a user that has privileges that you could use to get a foothold within an organization if it is valid. So when we need to figure that out, we start by querying the GitHub API. So the way GitHub works with personal access tokens is there's a certain API endpoint you can query that when you make that request, in the response, you'll receive a list of OAuth scopes associated with that token, as well as the authenticated user that that token belongs to. So with one request, you can learn if a token is valid and what permissions it has when the user created it. Additionally, there's more API endpoints that allow listing the organizations that an authenticated user belongs to. And the GitHub API is extensive, so we'll go into what more you can learn and how you can use that knowledge to gain a foothold on self-hosted runners. So towards the end of the talk, we're going to be releasing an open source tool that automates the entire process, both enumeration and attack. Finally, what about fine-grained personal access tokens? This changes the enumeration process just a bit because unlike classic tokens, fine-grained tokens don't return a list of scopes associated with them as part of the API response. So GitHub token scopes are set on creation. They can be changed later, but typically developers create a token, set scopes for it, and then leave it at that. There are a numerous amount of options for scopes. There are organizational admin scopes, enterprise admin scopes, scopes for very specific actions such as deleting a repository or modifying a wiki, for example. For the purpose of our attack path, the important scopes that we're most interested in are the repo and workflow scopes. So the repository scope is like kind of a catch-all scope that GitHub uses for classic tokens that covers interacting with a single GitHub repository. So this covers things like your standard actions like pushing code, pulling code from the repository, as well as if the user is an administrator on the repository, performing administrative actions on that repo, like adding a collaborator to the repo or deleting branches and such. So the workflow scope covers permissions related to GitHub actions. So if you want to make a change to a workflow, meaning the actual YAML file itself, and have that change reflected in GitHub so that when the workflow executes next, there's different code execution, you need that workflow scope. Otherwise, repo scope only allows you to make changes to the code within the repository, not the workflow. So one thing here is also GitHub Enterprise organizations and single sign-on. So for organizations that are paying for GitHub's enterprise level plan, which is their most expensive plan, they are able to require developers to explicitly authorize classic personal access tokens they create to that organization. So developers would create the token and have to click an additional button to grant access to that organization. And at that point, they will have to re-enter their two-factor authentication. Again, this is only once. After that, the token has access and it no longer needs to be re-authenticated to that enterprise. So this is not broadly used and not on by default. So a scenario is that a developer can create a classic personal access token for something they're working on the side and not related to their employer's projects. However, because the token is associated with the user, and if they gave it, say, repository permissions, then an attacker could take that token, if they were able to compromise it, use it to enumerate that developer's employer's repositories, and then perform malicious actions against that developer's employer, even though that token was initially only meant for a personal side project. So there's an important distinction about token scopes. Scopes are associated with the user that created the token. So if a user is creating a token, they can create a token with every single scope, enterprise admin, org admin, even if that user isn't an administrator of anything. So from an attacker's perspective, we need to figure out what the user is actually able to do within any organization that may be a member of. So for that, we need to perform additional enumeration beyond just learning about the scopes. So this kind of leads into API-based enumeration using GitHub's extensive and extremely well-documented API. So with this API, pretty much anything that you can do on GitHub, with a couple exceptions, that you can do via the web browser, or even with the pure Git command line, you can do using their REST API. You can do actions like downloading historical GitHub Actions run logs as zip files that you can extract later, and you can fork repositories, you can create pull requests. There's even very low-level API calls that GitHub exposes that allow you to directly interact with the low-level Git file structure that backs up a particular repository. Within this, there are certain API calls that return different fields depending on the actual permission that the user has to an organization or a repository. So, and this is the behavior you can use to figure out what level of permission the user actually has, and then perform additional enumeration or attack operations depending on where you're going with it. So this is an example of enumerating if a user is an organization administrator or not. So if the user does have that administrative access, then a field such as billing email, which is something that only an administrator can see for an organization, will be present in the response. If not, then that field won't be present. And the screenshot might be small for some people, but essentially GitHub even documents that, where it mentions that the type can be a string, but it can also be null, which means that's a good way to look for different responses within GitHub's API that could be used for determining what access a user has. So, and this is a technique that would need to be utilized to enumerate whether a fine-grained token has access to an organization and particular repositories, because you can't learn about the privileges, and also certain API calls like listing all organizations associated with the user might not work because that token might only be authorized to a specific repository within a specific organization. So additionally, the same technique works with discovering the privileges that a user has for a particular repository. So the scenario here is where you've obtained a token via a compromise, you've now listed all the repositories, and now you're trying to figure out which repository the user can actually make changes to further your attack. So if you call the repository list endpoint, then, or you just query a single repository, within each repository object in the API response, you'll have a permissions field, and that'll let you quickly learn whether the user is administrator, whether they have write access, or they can only read from the repository. There's additional fields like maintainer that'll also be present depending on the user's actual permission. Now, all of these actions, that created a lot of noise, right? You learned so much about an organization, you learned whether a user is a member of a particular organization, and you now know all of their repositories. Nope. With GitHub's current API, all of that does not create any noise, with some exceptions. So GitHub's audit log focuses primarily on state-changing actions, especially administrative actions like adding a new user or deleting a repository. A lot of the actions that are commonly associated with normal usage of GitHub don't generate audit log events. There's also no way for organizations to know when a classic token associated with the user was last used to access their resources. So, kind of looking more into these logging blind spots. The vast majority of GET API requests do not generate any audit logs. This includes when it works and when you get a 403. One exception that would be commonly used by an attacker is downloading a zip archive or a tarball archive of a repository. That does generate an audit log event. However, GitHub has other API endpoints that allow you to directly get the repository contents and get the git blob raw git blobs, but those don't generate audit logs. So an attacker could use API calls to do the same thing and bypass that particular log event and get the same knowledge. Git clone operations, which is directly using the Git command line and Git protocol to interact with the GitHub repository. So Git clone operations, Git push, and Git fetch are not logged unless an organization is paying for the enterprise plan, which again is their most expensive plan. And even then, to access those logs, that enterprise needs to ingest GitHub's REST API and pull down those log events, because the normal log UI for audit log events won't show the Git clone logs. Additionally, events like when a workflow is created are only logged and queryable by enterprise customers, and again, they need to use the REST API to get that audit log entry. So an attacker that pushes a workflow and that executes on a self-hosted runner won't actually be visible to an organization unless they're actually specifically ingesting that event. And some other things that are present. GitHub has a lot of defaults that are not enabled that you need to make sure as an organization that you're actually setting. So logging IP addresses associated with audit logs is very important. But by default, and this is likely due to privacy reasons in different countries, you need to actually go in and enable IP addresses to be included in GitHub audit logs. So by default, if someone compromises a token and performs an audit log generating action from another country, the organization won't have insight that that action was performed like from Russia or something like that. So this kind of leads into something else. If you want security, pay up. So in a scenario where an attacker compromises a developer's personal access token that has the repo and workflow scope for a smaller company that is only on the Teams organization, but they still need to use self-hosted runners, that attacker can use that token and gain all the knowledge they need to figure out what repository to exploit, and then push a payload that gets them command and control implant execution on a self-hosted runner, and now that organization's network is compromised. This will generate 0 audit log events from GitHub. The only insight that organization would have would be things on that runner itself. So, you know, it's always, I don't think it's a very radical idea, but, you know, people have different opinions, but, you know, I don't think offering a feature and then requiring, you know, the most expensive plan to be able to fully secure it is a good idea. So why does this all matter? If an attacker compromises a sufficiently privileged GitHub personal access token, then the first detectable action is malware execution on a self-hosted runner, which will then and very likely lead to privilege escalation attempts, lateral movement, and that is already a significant security incident for most organizations. So with that, I'll hand it off to Mason to talk about enumerating for self-hosted runners.
Thanks, Adnan. So how do we actually find where self-hosted runners are being used? So they can be applied at various levels at an organization. They can be applied in the enterprise, at the organization itself, or just at specific repositories. Now, listing for where these runners are present does require sufficient privileges. So you have to be an enterprise or org admin to look at those levels, or be an admin to the repository to check for a specific repository. Alternatively, with just read access, any user can download the run logs for historical actions, executions, and check for self-hosted runners there. GitHub actually explicitly denotes whether a self-hosted runner was used or one managed by GitHub. So how can we actually go about attacking these self-hosted runners? So by default, as we mentioned before, the GitHub self-hosted runner application provides very little security for the organization. In fact, it's 100% the responsibility of the organization to secure those runners. At minimum, we need a token scoped with the repo scope to conduct an attack. So what will these attacks look like? Now, again, this depends on the scopes of the token. If we have the repo and the workflow scope, then we can just push a malicious workflow or update an existing workflow to run whatever commands we'd like on the self-hosted runner. Alternatively, if we only have the repo scope and are unable to edit the workflows directly, we can just look for cases where code inside the repository is called by the workflow. For example, if a script is present and called by the workflow, we can edit that script, or maybe even edit unit tests. Now, how can we turn this execution into persistence within the network? So one of the most common tasks, as we mentioned before, is doing Docker builds or pushing up Docker images inside of your GitHub action. We can leverage this as a persistence mechanism. So this will give us, first, a really easy priv-esc, since Docker is typically running as a privileged service on the system. Additionally, we can just run a detached Docker container, and when the workflow completes, we'll maintain persistence on that system. Alternatively, if Docker isn't present, we can actually just run a detached process. Now, by default, GitHub Actions will clear up any processes spawned by the action, but there's actually a really simple environment variable you can set to an empty string, and any backgrounded processes will not be cleaned up when the job finishes execution. So we've mostly talked about obtaining unauthorized access through classic tokens, but what about public repositories? So we found in many cases GitHub's stern recommendations about not using self-hosted runners isn't followed. In fact, we used the code search API to find a large number of repositories that are public and using self-hosted runners. To attack these repos, we have to think about things a little bit differently. So by default, if we open a PR for a public repo and update a workflow, this isn't going to execute. We can set the on-pull request trigger in the workflow, and again, this still won't execute. And that's because GitHub added some additional controls for PRs for repositories. the execution is blocked until a maintainer or someone with the sufficient access to the repo goes in and approves that execution. Now, by default, this is only set for first-time contributors. So a really easy attack path in these situations would be to get a simple documentation change to a README or something of that sort merged into the repo, and then performing this attack. So to automate all of this, we've developed a tool called Gato, or the GitHub Attack Toolkit. This is written in Python and runs on most Unix environments. It's also released under the Apache license version 2, and we have 3 core modules: search, enumeration, and attack. This is available on GitHub now. So the search module is used to find public repositories where self-hosted runners are being used. The enumerate module is used to identify repositories that might be vulnerable. And finally, the attack module is used to automate a full end-to-end attack chain on these self-hosted runners. And so from here, we'll give a quick demo of that tool executing.
All right. To start off, we're going to look at how the search module from Gato can be used to search for self-hosted runners within public repositories and then perform a deeper enumeration of those repositories and learn things like the name of the self-hosted runners, the host name of the self-hosted runner, as well as the contents of the YAML files that those runs use. So Gato has a pretty straightforward command line interface. It supports HTTPS and SOX proxies, and in this case, for the code search module, we just take a single parameter, which is the target organization. And this part of the tool is just a lightweight wrapper around that code search API that was mentioned earlier. So to use the tool, you just have to give it a personal access token. For the search module, you can give it a token with 0 scopes because it doesn't actually need anything to run. In this case, we've ran it on the Microsoft GitHub organization and obtained 16 repositories that have the string self-hosted within the workflow files. So just going to quickly write that out to a text file and then use the enumerate module to enumerate every single repository in that list. So after starting that command here, so this one's going to need a personal access token with the repo and workflow scopes because those API calls require that. Again, since it's public repositories, you can just create your own personal access token with those scopes to use this feature. So in this case, we're going to run it on those 16 repositories and also set a flag called output YAML. What this will do is every YAML file that it discovers that has the on self-hosted trigger, it'll just save it off so you can look at it later. So this part of the video is sped up a bit, but essentially what it's doing is it's performing a clone of every single repository, but it's using a sparse checkout, so it only gets the .github directory, so it's a lot faster and you're not downloading hundreds of megs of other content from the repo. It's also downloading historical actions run logs, extracting the zip file, and then parsing out the machine name and runner name of the self-hosted runner. So that'll tell you that it used the self-hosted runner in the last 90 days and the name of the machine. So that sometimes could be a host name or IP address, depending on how organizations have it set up. So you could develop a good target list using this. And then after this completes, just going to show that we've saved off all the YAML files. Again, it might be small for most of you in the audience. However, in this case, what I'm doing here is just opening up a build CI container YAML file and looking at the different steps in the jobs. So in this case, Docker is being used in this workflow, so it means that if someone were to get execution on that self-hosted runner, then there's a good chance that user is in the Docker group and they could potentially perform actions for privilege escalation. So with that, I'll hand it off to Mason to talk about the enumerate module in the case of a hypothetical compromised personal access token.
Matt, actually.
Sorry, Matt.
It's okay. So The enumeration module of Gatto also has a capability to, if you're on a red team engagement or pen tests, etc., what do you do if, did this thing restart?
Space. Maybe it did, yeah. You might have to skip over.
Yep. 1 second. Is this, yeah, we're doing, okay.
No, yeah, just skip over that part.
Yeah.
You're good. Yep, right there.
Okay. All right. Excuse the technical difficulties there. So the enumeration module of Gatto also has a self-enumeration module flag that essentially if you come across a compromised pat on a red team or pen test, et cetera, or whatever, you can start to enumerate what permissions are associated with that pat. It will go through and tell you the username that pat is associated with, the organization, and it will then look at the scopes that are attached to that pat and all the repositories it has write access to. So we can see here, well, it's a little small, but you might be able to see here. The authenticated user here, ShmooCon demo, the scopes that are associated with the pat that we pass to the tool are repo and workflow, and this pat, or this user, belongs to the Shmoocon2023 demo organization. Once it's identified this, it then starts to enumerate the repositories within this organization, and it finds 4 of them. The most interesting one being this Shmoocon2023 demo private repo 2. It notices that we do have push access to this repository. We do have a workflow scope assigned to our pat, and it has, by looking through workflow run logs and looking at the workflow YAML file, identified that it is using a self-hosted runner. So after it identifies all this, it suggests to the user that you have the workflow and correct permissions on this repository to execute a custom YAML payload and execute, or essentially shell this self-hosted runner. When it finds repositories like this, it also downloads the workflow file, in this case, this demo CI YAML file. That way the user can look through this before continuing with the attack chain. And to show the fun of the attack chain, I'll let Mason take over.
Thanks. Yeah, so once we found a vulnerable repo, we can actually go about attacking it. And so we've built in a number of different options for automating this attack. You can set things such as the name of the branch that you're going to push to, or the name of the file, or just even the command that you want to execute. And so here we will execute an attack targeting that same private 2 repo that we identified with the enumerate module. We're specifying the execution to run uname and to cat out etc password. We're also setting the commit message and specifying that the workflow file should be called evil. And so once we execute this, we'll see how that attack flow works. So it's a bit hard to see, but you'll see quickly that we push up a malicious branch, and then we wait for GitHub Actions to queue our execution. So once the self-hosted runner picks up, we'll wait for that execution to complete. And just a few seconds later, that execution will complete successfully, and we've downloaded the run log for that execution. Now we can unzip that and take a look at the logs themselves. And we'll see, once we get this open, that both the uname and the cat etc password executed on that self-hosted runner. Now, if we hop over to the GitHub side, we can take a look at what that looks like in the web UI. So if we pull up that private repo 2, go to the Actions tab, you can see our execution is in the logs. Now, by default, this won't get deleted, but we did add the option to delete this execution log as well, so that there's no trace that the attack executed. Anyone can go in and take a look at what executed and what the output was, so keep that in mind when attacking repositories and dumping sensitive information. Additionally, anyone can look at the actual workflow file itself if this isn't deleted. And that's all we have for a demo. So to wrap things up, we just wanted to quickly note that these concepts aren't just applicable to GitHub Actions and really can be extended to a number of different CI/CD platforms. Personally, we've targeted GitLab shared runners in a similar fashion this year. Now, GitLab does add a few extra controls and some better defaults in some cases to prevent this from happening, as well as some good documentation around that. But it's not always the case that GitLab shared runners are secure as well. Additionally, there's other classic targets such as Jenkins and TeamCity and a number of other CI/CD platforms that people have been exploiting for years. Finally, just wanted to quickly shout out Marcus Young for his work on the Zucker Punch stuff last year, as well as GitGuardian's GitHub Actions security cheat sheet, as those were both useful to us when doing research for this talk. And we'll end with any questions.
Nope, over there.
Sure. Yes.
I had a question about GitLab. You kind of covered it at the end, but does the logging for GitLab do any better than GitHub? Like, did you see the last time a key was accessed or used to access years ago with GitLab because it's GitHub?
Sure. So the question was, how does GitLab shared runners work on the logging side? We talked a lot about the gaps on GitHub side. Do you know the answer to that, either of you? I'm not sure. We're not sure off the top of our heads, but we'll definitely look into it. Yes.
These experts assume the malwares and the GitLab runner. So how we get the VPC, like, are you just not worried about that? You're just assuming they're in there.
Sorry, say that again.
You're just assuming the GitLab runners are affected or something like that, that they're that actors that they need to access the runner. So if you already program, they already have a secure network, it wouldn't have to matter, right? The GitLab runners are the private VPC.
You want me to?
Yeah, sure.
Yeah, so the question was, if the network is already secure and we compromise a GitHub runner in this case, what is the risk there, right? So there's a few things. It's definitely up to the organization if they secure it correctly. You can secure these correctly. It's not out of the question. It's, from what we have seen, kind of rare. There are cases where, let's say the thing is completely isolated. What we can do is, if we have privesc on that box and let's say it's running Linux and we get root, we can start to look at process environment variables and dump from memory to see as other jobs are executing, we can start to dump secrets from them, etc. So if it is properly secured, it is properly secured, but that's not what we've seen in most cases. I think there was...
Yeah, so in this case, we did not share anything with GitHub. Yeah, so the question was if we shared any of this research and discoveries with GitHub and if they had any reactions. So as far as sharing anything with GitHub, so nothing that we cover isn't already publicly documented by GitHub. Some of the documentation isn't very clear, especially regarding the fork pull request behavior. So this is just kind of going over stuff that's already public. So we're not disclosing any vulnerabilities in this case. So no, we did not have any communication with GitHub. Right. Right. So the question was make sure I'm remembering correctly. The question is if we can restrict the usage of a PAT based on the IP where it was issued. And what was the other part of your question?
And the other one, and/or can you just limit the life of a path, so even if they get one, they have to maintain persistence on wherever they got initially to get the next one?
Right. So regarding limiting the lifetime of a personal access token, so upon creation, the expiration window for that personal access token can be set. Regarding the limiting where it was issued from, so GitHub does not have that restriction in terms of like IP source for issuing the personal access token itself. However, fine-grained tokens, which are in beta right now, have a lot more granularity when it comes to what resources they can access. And organizations also have more insight into the fine-grained tokens that can access their assets. And they can actually revoke just access to a particular repository. So the fine-grained token is still valid, but it can no longer be used to access that organization's repositories.
Yeah, so this is a great talk. I think Matt and I did this together like 6 or 7 years ago for large silicon manufacturers and could see some things that were changing. With the introduction of the personal access tokens, they, like the fine-grained personal access tokens, they also gave us the ability to basically forbid personal access tokens for an organization. So with that, I was kind of pushing my organization towards like, hey, everybody use SSH keys. Can you still use runners with like SSH key access or like personal access tokens? Like, I don't know, obviously an SSH key can't do all those things on the API, so I don't know if there's like additional kind of attacks there that you can think of.
So the question was, if an organization has moved away from personal access tokens and is just having developers use SSH keys to interact with repositories, could similar attacks be carried out on self-hosted runners? So again, the API actions can't be done with the SSH access. However, the one way something could happen is if an organization is using self-hosted runners and that SSH access is used to push code to a repository that already has a trigger that would allow code to run on a self-hosted runner. And as we discussed with being able to modify code that's checked out and then executed as part of a build that's on a self-hosted runner, that could be used to conduct a similar attack.
It did. Nice to see you. Yeah, I think one of the big differences too is that with the PAT, you can do a lot of the enumeration where you can understand exactly what your permissions are, what repositories there are. To my knowledge, at least with the SSH keys, I don't know if there's a way to enumerate repositories that you have access to. Is there?
No, you'd have to learn it from other contexts.
Yeah, so it definitely limits the context. So I do think that's probably the more secure option, but it does limit the functionality. Yeah.
I believe it is, yeah. I think the runner registration token is one-time use, and then it's really easy to acquire new ones, but the token for the runner itself is one-time.
Would there be something, would there be a situation you could see where you would want to register your own malicious runner for the organization?
That's definitely, so the question was, would you ever want to register your own malicious runner? So there's definitely some opportunities for grabbing secrets that way. You would definitely need sufficient privileges to the repo to do that, and there might be some other interesting attack paths that that would kind of fall out of that already, but it still definitely is an interesting option for getting secrets. Cool, thanks everyone.
Yeah, thank you guys.
Thank you.